anybody who's into electronics engineering has been using scopes for probably as long as they've been into electronics engineering. Why do we need to revisit this topic? Hey, what's up, guys? Welcome to Embedded Toolbox, the interview series where we try to save the world by solving one engineering challenge at a time. And today we are trying to solve a challenge that most of you thought you already solved, which is just debugging with oscilloscopes. And to broach that subject, we brought on Mike Schnecker, who's the business development manager at Rohde Schwarz. How you doing, Mike?
Pretty good, Brandon. Thanks for having me on.
Sure thing. Thanks for joining us. So like I said, most engineers or anybody who's really been interested in electronics engineering has been using scopes probably since they realized they were interested in electronics engineering, right? So why do we need to brush up on the basics, and why do we need to go back to basics with scopes now?
I think, you talk about people using scopes. I think they're used and often abused. So maybe it's good to review some things every once in a while.
So what are some of the things that people use and abuse with scopes? It's sort of like a necessary evil, right? Let's take as many shortcuts as we can.
Yeah, that's the thing I always talk about. Scopes, sort of the one instrument no one wants to use, because when you turn it on, you've got a problem you got to fix, right? So hopefully things work out of the box. Just setting up scopes is not often trivial. A lot of people forget basic things like sample rate, memory depth, making sure that the signal is properly positioned on screen. Seems like trivial stuff, but it makes a big difference in what you get as a measurement. So it's always good to review those things, I think.
Very good. Well, a great place to start off would probably be with something that most embedded engineers, at least, are really familiar with doing, which is debugging serial protocol. So what do you say we start out with I2C debug as a baseline?
Cool. Yeah, that's great. So I2C is a pretty common interface. And one of the neat things about oscilloscopes is most of them have I2C decoders, where you can actually decode the waveform into a series of ones and zeros bits, and then actually convert that into words and commands. And then, of course, a lot of the other scopes, not every scope, but most of the higher end ones will be able to trigger on specific data patterns and words. So it's a great way of debugging software hardware interfaces, right? We have a scope right here that we can show you that on.
So before we get go any further, what scope are we going to be using? Obviously, Rohde Schwarz has scopes, so why yours, and what are we gonna see in this one that's not available in others?
So one of the things that we brought to the market is the RTO6, which is our newest instrument in the RTO series. The RTO is a pretty powerful scope. It does not only time domain stuff, but it has a really powerful spectrum display, so you can actually look at it, use it kind of as a spectrum analyzer as well. And we've got a number of built-in protocol decodes that are actually implemented in hardware, so you can actually trigger on different protocols. The other thing that we're really bringing to the market, which I think is really significant, is a much better user interface, larger screen. Everybody wants bigger screens. You're looking at lots of waveforms, so you need more real estate to see things. So hopefully you can see what looks like an oscilloscope screen.
Yeah, that's
right now
that's pretty clear. It's really high resolution.
This particular one's a 15-inch HD display, so lots of real estate. Everything's big and bright. One of the other things that we've done with our scope, and this actually gets into the complexity, I think, oscilloscopes have added so many features that most users would probably tell you they're too complicated to use. And that's really the challenge for scope companies, trying to figure out how to add all these features without making the user interface overwhelmingly complex. And what we've done is, historically, we've gone through like Windows type interfaces where you have the pull down menus and all that stuff. And the next generation, which is what the RTO6 is gone more towards an app type format. So something like you use on your iPad or your iPhone, where you actually have this single menu system in the bottom right corner here. And I'm just going to reach over and tap on that. And there's a pop-up menu that has essentially all the settings stored together. And so you have your basic, vertical and horizontal timing settings that you would use. But you also have a really neat feature called apps, where you can put a lot of the applications, the more advanced things you can do. And as you can see, there's an enormous amount of analysis that you can add into scopes. And this is all software stuff, so we can add on later on as these things are developed. So what I was going to do really quickly is just kind of show a waveform on the scope screen. So let me cheat here. I'm going to actually turn on the two waveforms that we're measuring. I have a little board here with an I2C signal on it. And I've connected the clock to the channel 1 probe and the data to channel 2. And the way I'm going to cheat is I'm going to use something I don't recommend anybody doing, but I'm going to do it anyway. I'm going to press the auto set button. And the auto set button is a very nasty button because while it is one of the things that people like because it gets things set up very quickly, it doesn't necessarily pick the right settings. So if you let this run for a second, you're going to see it's going to get a waveform on screen, but the problem is it's sort of don't know what's going on because it usually picks the wrong horizontal settings. I'm just going to turn the horizontal time base out a little bit to get a better view of what's going on. And you can see the waveform there. It looks like a burst of two waveforms. There's a yellow one, which is channel 1 is clock. The green one is channel 2, it's data. On our interface, you can actually drag and drop. So I can actually take this box in the bottom left corner and drag it out and split the display that way. So I can actually do drag and drop to set up different display landscapes. And this is something that's unique to the RTO, but it's kind of a fun thing to play with. So right now they're kind of separate grids. I can actually slide it out and put them on the same grid on top of each other. But what we would like to do, let's say I've got an I2C, this is an I2C bus. I want to actually, decode it in something I can understand. So our scope, along with a lot of other scopes, has the ability to decode this. Let me just show you real quick that the neat thing we can do with our display. So right now the waveforms are superimposed, but maybe you would like to see them separately. In our scope, you can just drag and drop to create landscapes, and you can actually resize them just by grabbing that with your finger and sliding it up and down. So you have this ability to set up different landscapes on your screen just simply by dragging and dropping, which I think is really cool. Makes life a lot easier, and sometimes, even a little fun when you're debugging. So I'm gonna drop them on top of each other. We're gonna go back and we're gonna set up that decode. So I'm gonna go back into the menu, select apps and my protocol, and I'll select I2C, and immediately it just turns that on. Now you don't see a decode, it's actually a question mark. Well, that's because if you look in the setup, you'll notice I have the clock and data wires swapped logically in my setup. So I'm just gonna go in here, select clock is channel 1, data is channel 2, and then immediately it's decoding stuff. And let me just pop this menu down real quick. So you can see there's a table of decoded results, and then superimposed on the waveform is the decoded data. This is a write and a read. It's writing and reading from address 10 hex, and you can see the read value. It's just the bright purple on the far right. It's kind of changing values all the time. In the table, which is kind of cool, you can actually see each packet decoded with its hex value and its address. There's also a label field here, and that can enable you to actually edit and create your own labels for specific addresses. So you can make it actually readable, like what device on the bus is being talked to at that moment. You can actually read that stuff out. Another neat thing with my drag and drop is I can actually move this and park it down here so you have a table separate from the waveform. The last thing we can do is we can actually trigger on specific address or data values. So right now, if I go into the trigger, you'll see it's just triggering on channel 2, I think, right now. So we're going to tell the scope, hey, trigger on the serial bus, trigger on that bus we've defined. And so now it's switched over, and you can see it says, okay, we're triggering on a start now. So you see how that thing is now lined up perfectly at the beginning of that packet every time, because now the trigger system is saying, hey, trigger on that logical value. And you could actually trigger on a number of different things for this particular protocol. You can trigger on a stop, a NOAC, that is a missing acknowledgement, which is great. So if you want to make sure that your devices are all acknowledging, you can look for no acknowledgement and see if those things are alive on the bus. You can trigger on specific addresses and or data values. So a lot of flexibility in this thing. And again, a lot of scopes have this feature. I think ours is a little bit better than everybody else's, but hey,
What if we want to go a step further? What if we want to look at, something, for example, like the timing between all of the triggers that you're dropping in there?
Yeah, so that's kind of an interesting feature. So one of the couple of things we can do in our scope is you'll notice that on the table there's actually timestamp for each packet. So there's a couple of ways to deal with this. If I want to see multiple packets, I can increase the time scale, and then I'm seeing right now 5 packets on the screen. You can see the tables expanded below, and we've got the timestamps for all the different packets. But let's say those packets are pretty well spread out and we want to collect even more of them. One of the cool things that we can do is we have something called history in our scope. So the scope is triggering and repeatedly triggering over and over again. And when we acquire those waveforms, we're actually not throwing the old data away. We're storing sequentially all the time. So it's like a big, deep memory, and it's writing through that. If I press the history button on the front panel of the scope, it stops the scope. And up here in this little table, it says history. There are 1,833 acquisitions sitting in memory. And I can dial back through them one at a time. So this goes back 10 milliseconds and then 20 milliseconds. So every time I've captured a packet, it's timestamped it here. And this is the data from that particular acquisition and decoded values. So if you want to collect tens of thousands of bursts of data into a bus, you have the ability to do that in real time here. So you can actually play it back later on, look at each packet. And even more interesting is you can actually cause the scope to search for certain errors within that set of acquisitions. Say, you know, how many times did I write to this address? And it'll actually play back the data and capture the ones that are at that address. So, you know, cool things you can do with digital scopes. I mean, everything in memory, you can always play it back. The nice thing about the history is the minimum gap between acquisitions is as small as 300 nanoseconds. So you can do some pretty fast stuff on it. So there's one other cool feature that's kind of unique to our scope. So I thought I would show folks that. One of the things that is really important in oscilloscopes is triggering.
Right.
There was a time when you didn't have triggers in scopes and the waveform would move around, right? So what I want to show you is something that we do is called digital triggering. It gives you a lot of sensitivity and very good stability. This is that I2C clock we were looking at before. And what I wanted to do is set this up kind of in a normal setup that you would have. Like a and 20 gigasamples per second. Okay. All right. So it's a little hard to see on the screen that you're looking at, but if you look at this is sort of the beginning of that I2C pulse. You can see right over here, there is a very, very small, and I don't know if my mouse can show you that. There's a very, very small like glitch in the waveform. It's barely viewable. What I'm going to do is I'm going to actually zoom in on that. So I can select my zoom control and I can zoom in real close. And so you can see what I'm talking about here. So that little tiny, almost discontinuity there. That's about 18 millivolts. And what I'm going to do is I'm going to trigger on that. And you're going to say, how do you do that? Well, basically bring the trigger up and here comes the trigger. Now, one of the interesting features of our trigger is, see a little band there, that's a hysteresis band, so it's a noise rejection feature. So if the signal enters into that band, then it triggers when it exits that band. Problem is right now, I'm at the resolution limit of the scope, so I really can't do much to trigger on that because I can barely resolve it with my A to D converter. And if you're on a typical oscilloscope, you're kind of dead in the water here because there's no way you can get that better. You can filter it, but the trigger doesn't see the filtering. It's always post-acquisition stuff. So what I'm going to do is I'm going to turn on a feature here that we call HD mode, and it allows one to trade off bandwidth for resolution. So right now awesome. It's set to 1 megahertz. I'm going to crank it to 3 megahertz. Pretty cool. So as you can see on your screen, that resolution increased. The trick we're using is kind of a standard technique that's used for A to D converters. It's actually used for all audio ADCs. You essentially use oversampling and filtering to get more bits. That's what we're doing in the scope. We just take advantage of the oversampling. This is a relatively narrow band waveform. But what's really cool is the trigger itself can now see that filtered waveform. So you can see the trigger point is sort of this arrow right here. What I want to do is I want to trigger on that guy. So I'm going to, first thing I want to do with our trigger is I want to turn off that hysteresis. So I'm going to turn that off so that it's a regular threshold now. You can see the dotted line. And I'm just going to turn that up and it's triggering now on that little tiny 18 millivolt pulse. And if you want to get an idea, this is the zoom waveform on the bottom. We just drag that down. What I'm triggering on is that little tiny pulse in the middle reliably. And we're doing that because our trigger circuit isn't really a circuit at all. It actually uses the digital data from the A to D converter. And even after the filtering, we're able to get the effect of that filtering applied to the trigger. So that's pretty cool.
Wow.
I have fun playing around with that, and it's I think a useful feature.
So obviously we looked at a little bit of the performance there, Mike, of the RTO6. What are some of the key features that the users of scopes need to know about the RTO6 in terms of performance?
So yeah, basic specs of the RTO6. So, bandwidth, sample rate, memory depth things. It has bandwidths available up to 6 gigahertz, starting at 600 megahertz. So you can, buy in at 600 megahertz, lower cost. There's software upgradability and bandwidth, so you could upgrade the bandwidth later on. Standard memory is 200 megasamples per channel, which is very deep for this kind of an instrument, but we can upgrade it up to 2 gigasamples, so lots and lots of memory. Memory is important because it's your time base. Sample rate is of 10 gigasamples on 4 channels, 20 gig on 2. We can interleave on the higher bandwidth scopes to a higher sample rate, so you can get more sampling. The resolution, the native ADC is 8 bits. However, there is an HD mode, which allows you to get up to 16 bits of vertical resolution. That 16 bits, that resolution is not only on the display, it's also used by the trigger. So when you turn on HD mode, the entire scope turns into a high resolution oscilloscope, which is kind of unique because it's very transparent. Just turn it on and just kind of runs. It's pretty good.
Just watch the Super Bowl on it, right?
Exactly. Hey, 15-inch display. It's going to be a great game. Let me tell you. In fact, I might watch it on the scope this year. But
one of the things that I've been noodling while we've been going through this, Mike, is the fact that you're talking about this being, a modern, smartphone or touch-like platform with apps, and the way that you can upgrade, from the performance. I wonder if you are, doing something a little bit more, demanding in terms of the scope, what you could use the scope for, or whatever your use case is. Do you have the ability to upgrade, its capabilities to do different things? Maybe if you're doing, network testing, or, just something that requires a little bit more performance, or a little bit more from the application side, like an app?
Yeah, so that's a good point. There are a number of apps that you can get on the scope. There are features that can be added. They're just option keys. So let's say you wanted to do advanced jitter analysis or timing analysis. That's an app you could just add to the scope, and then you have a full decomposition of jitter. If you're looking at digital signals, let's say you might be high speed and you want to recover a clock and do eye patterns and stuff like that. That's another option. It can be just turned on. And we have a number of standard compliance apps for different standards. So for like Ethernet or PCI Express or things like that, you can actually get an app that does standard compliance tests for those things. So there's a lot of stuff available. And of course, we're writing more every day. So trying to make the features as helpful as possible to anybody who wants to do these tests. But yeah, it's an ongoing project, really.
That's awesome. So, that's a pretty awesome overview. I want to thank you for your time, but before we go, just want to ask one question. Do engineers need to upgrade their scope game?
Well, you can ask me. Of course, I think they need to upgrade the scope game. So let me tell you, if you've got an old analog scope with a green trace on the display, it's time to upgrade, because the digital world is a lot more complicated than it used to be in the old analog days. And yeah, there's a lot of great instruments out there, including from us. And I think, yeah, if you've not upgraded in the last few years, it's a good idea to look around and see what's out there.
Let's be honest, like we said back at the top, people don't want to spend that much time in a scope. And it looks like with RTO6, it just makes things organized, simple, easy to use, and allows you to get through your debug pretty fast.
Exactly. And I guess that's kind of the way I look at it. Fastest time to the resolution of a problem. So with all the speed and features on the scope, it doesn't take you long to find and isolate the problem you're trying to find.
That's great.